Find an expression for the acceleration of a cart down an incline, ignoring friction. So I'm going to start, since we already have the sketch there, that's kind of step one in the flowchart we looked at recently. So I'm going to go to step two, which was the FBD. And definitely there's going to be a force of gravity there. The normal force is going to have to be at a bit of an angle here to reflect the fact that we're on an incline. Do I need any other forces? Well, it says that we're ignoring friction, so that means the only other force that I can see there is the interaction between the cart and the incline that it's on. And if we're saying this thing's moving down that incline in a way that there is no friction, then there's nothing else to add really here. So okay, what's the next thing that we have to decide? I don't know if anyone wrote down that flow chart. So let me see. We've got FBD. I think we have to decide inertial versus accelerated now. And since we're clearly talking about a cart that's accelerating down an incline, I think this is in the accelerated category, which means I'm going to wind up doing something with Newton's second law, F equals ma. So once I've made that decision, okay, this is clearly accelerated, then the two choices are either, right, F net is equal to 0 or F equals ma, and I went with F equals ma because it's accelerated, right? I have my free body diagram. One thing I might like to add somewhere, I mean, I can't really, it turns out with my setup here, I can't draw on this picture, but let's recognize, since it is accelerated, there is an acceleration here that's down the incline, and I'm just going to draw that somewhere here to the side of my picture, just an acceleration vector that's meant to be kind of parallel with this incline. And so again, there that is. Maybe something else worth adding, though. I'm going to maybe resketch this for a second so I can add some other information. I mean, this question, the way it's worded, is maybe a little bit vague, but I think I'd like to define or be able to define some quantities here kind of on the fly as I go. And one of those is this incline should definitely have an angle theta. The cart, of course, should have a mass m, although that may not matter for the result that we're going to get here. So I'm just going to put those things in there because those are things we can assume probably would be there, and if this problem had actually asked us to calculate a number, would have had to maybe give us some of those values, perhaps, right? Anyways, we have a choice now, though, right? Because we can choose to either analyze this with geometry or we can choose to analyze this with components. I think in my flowchart I also said something about a coordinate system, and maybe if I chose to use geometry like a triangle, I might not even need a coordinate system. But if I'm going to go with components, I think I need to establish a coordinate system. And it turns out for this one, like if you look at these vectors I have that are involved here, gravity points straight down and in that sense is perfectly vertical and aligned with the y-axis, or maybe the negative y-axis. But the normal force and the acceleration are neither aligned with the y direction or the x direction perfectly. Now it turns out this is kind of a clue that maybe an easier way to do this problem would be to consider using a rotated coordinate system. So in my little sketch that I put over here, I'm going to draw kind of a set of x and y axes, and the only purpose these really serve is to kind of tell me how I've modified the usual direction for x and y. And what I've chosen to do, even though I didn't draw it quite perfectly, is I've chosen to have x be parallel with the surface of the incline and y is at right angles to it. So in other words, it's been slightly rotated to reflect the incline. And that's going to be cool because it's going to make the normal force and the acceleration vectors perfectly line up with either the x or the y-axis. And as this analysis kind of unfolds, I think that's going to be helpful for us. So let me go and write what I think should be the next step here. I mean, I've kind of been doing a lot of talking, a lot of thinking here. It's maybe easy to want to rush into writing a lot of detailed equations with a lot of trigonometry or something like that. But I'm just going to restate my F equals ma with the specific forces. In other words, recognize here's the vector equation that, according to the principle of Newton's second law, should connect all three of these vector quantities. At this point now, I'm ready to possibly consider, since I'm choosing components as my method, which component equation do I want to write? And that's, maybe a good question here is like, which one would, be the better choice? And I'm going to go with X as my choice here. And I'm confronted maybe immediately with a problem here of like, okay, what is going to be the component for this vector to put there? In other words, like maybe I'll just first write it down. We know from an earlier chapter that if I'm doing this, like really what I'm talking about is, I mean, this is kind of like what we did at one point, right? But really, if I look at this, like, okay, normal force is not in the x direction at all. So that one didn't even need to be there. So I'm just going to cross it through with a 0. The x component of acceleration really just is the acceleration. So maybe I don't really need this subscript here, and I could have just left it as an A. This could get a little bit messy. But this one here possibly gets a little bit tricky. So I'm going to look at that one in some more detail. Let me redraw my coordinate system slightly below here. And then what I'm going to do is I'm just going to kind of hang my force of gravity from that. I can move vectors around, so maybe I can hang them from coordinate systems if I want as well, like I just did there. And then if I look at this and I kind of say, like, well, what would the components of gravity be, right? Well, there'd be a component here. I'm just going to draw maybe sort of dotted line for one component, and there'd be another component there. And where would this angle of the incline come in? Now, I think my coordinate systems maybe rotate a little bit more steeply than my original incline was, but it looks like this is still the smaller of the two angles. And so I think that one is theta. That could be tricky to prove with geometry. I mean, maybe one way to see it is that the normal force is aligned with the y-axis, and the normal force should, I mean, you can connect, I think the normal force being perpendicular to this surface should have made that same angle with the vertical. And I think that makes sense that that angle would be the same as this angle here in this picture where we've moved gravity over to this spot and again kind of aligned the x-y coordinate system with the normal force and the acceleration. What that means is for the x direction is opposite to theta, and opposite is associated with sine. So what that means, I'm going to actually write for my x coordinates, since the magnitude is equal to the weight, and opposite corresponds to sine. This may be a bit of a leap that I'm doing here, but I'm going to say mg sine theta is what that component is equal to. Again, because I know the magnitude of fg is equal to mg. In other words, I labeled this fg, but really it just is the weight. They are both associated with each other. So the hypotenuse of this triangle here, this component triangle, is really equal to mg. And in that sense, this other component here would be mg cosine theta, should I choose to do the vertical components. I don't know if I'm going to need to, though, because this may be enough to answer this question, because it's asking us to find an expression for the acceleration here. And the thing to notice is I can divide the mass off from both sides, and the result is that the acceleration is equal to g sine theta. What's interesting about that is I said earlier, well, maybe if this had been a problem that it asked me to actually calculate a number for that acceleration, like what information would I need to have been furnished with? And the answer is just the angle and the fact that it's on Earth, because I need to know that it's 9.81 meters per second squared that I can safely use for the g part. But I don't actually need to know the mass of the cart. So sometimes I ask a question like that and people come and ask me, like, wait, don't you need to give me the mass? And it's like, no, do a little more analysis. You'll find out whether you do or do not. So I think, again, that's the answer right there. The slides are now I have in the slides here a slightly different path through to the same answer. Instead of doing components and using a rotated coordinate system, it's going to take a geometric approach and kind of analyze a triangle, which is also possible to do here, it turns out. So let's see how that turns out. It's going to start with the same FBD we just had. It's labeling it with words instead. But now it's going to take those vectors and find the net force by geometric vector addition. So there's normal force, there's gravity force, lined up or arranged head to tail, and that means the gap there represents the net force. But that net force, which really we could find from that, let me back up a second here. I've written down here that that net force is equal to mg sine theta. That actually can come from an analysis of this triangle by identifying that this vertex up here has the angle theta, and the fact that the net force is opposite to that, you get mg sine theta from that right triangle, similar to how I did over here. But again, here I was kind of thinking about components, whereas here I'm just thinking about the geometry of forces. And then it says here that since Newton's second law implies that F net equals ma, that mg sine theta I had a second ago would be equal to ma, and then the masses would cancel just the same as I did here. So in some senses it was not all that different, but on the other hand, conceptually, it definitely was a bit different, that alternative method that the slide showed for going through this problem.